randomized matrix.
Thank you, Daniel. How are y'all this afternoon? Digesting your lunch? So I need to shake you out of your torpor. So to begin, Raphael insisted on a quote of the day. So today's quote is from Julius Caesar. Upon crossing the Rubicon, he is reported to have said "Alia jactast," which means the die is cast. Can't go back. All right. So what are we talking about this afternoon? All afternoon. Congratulations. We're going to be talking about randomized matrix computations. I'm going to start actually at the very beginning with some discussion about what is a randomized algorithm and even some very basic examples connected to linear algebra computations. I've given some version of this tutorial several times already, and there is a detailed set of typed lecture notes which are available on arXiv at that address, which were written in collaboration with Anastasia Kireeva. So she played an important role in getting this material documented. You can also find that on my website. Okay, so warm up your brains. How many of you have encountered a randomized algorithm before in your lives? Okay, I won't ask for the people who have not, since I don't want to embarrass you. What are some of your favorites?
Polynomial identity testing.
Randomized quicksort. Okay, polynomial identity testing. We will arrive at that in a moment.
Random range finding.
Random range finding. All right, we'll talk about that later.
Hash tables.
One more time?
Hash tables.
Hash tables. Okay, great. So what is it that randomness allows you to accomplish in these settings?
Dimensionality reduction.
Dimensionality reduction. I think we'll talk about that somewhat later this afternoon. A lot of the time, it helps you do something efficiently, which is not easy to do deterministically. It can break symmetries or help you find things that are for example, not obvious to you, like a vector which is not aligned, which is aligned with the top eigenvector of your matrix, as in Mark's talk. Polynomial testing, we were able to avoid the bad set of points where the polynomial identity might not be true. All sorts of things. So we'll talk about the structure of this course. Sorry, I'm also digesting my lunch. Anyway, so the structure of this course is that we're going to talk about the following vision, which is not original to me. It's a community effort that dates back easily 30 years. Some of the early work was due to Ravi, who is here in the back. But there are actually examples in numerical linear algebra that date even farther back. And the claim is that randomized algorithms are indeed powerful tools for numerical linear algebra. And what I want to show you is that there are different ways that we can use randomness to design these algorithms. That there are fundamentally different phenomena that lead to effective algorithms. And I want to talk about some of those distinctive strategies. And for each of these strategies, I'm going to try and give you several examples of how that strategy plays out. Now, this is a relatively short presentation, so there's not going to be a lot of mathematics. It's going to be focused a bit more on ideas. And I'm not going to be able to include a lot of the details. So much of that is elaborated in the lecture notes. So if you want to find out more, I encourage you to start there. OK, so what are we talking about? So first of all, what is an algorithm? So an algorithm is a well-defined procedure for solving a well-defined computational problem in a finite number of primitive steps. Okay, so there's some undefined terms here that I'm going to leave undefined. The focus today is on what we call algorithmic randomness. And I'm going to make a distinction in a little bit with statistical randomness. So for an arbitrary problem instance, The algorithm will draw random variables, which are often called coin flips in this context, even though they don't necessarily need to be binary or, in our case, even discrete. And what does the algorithm do? It uses the outcomes during its execution to help solve the problem. Because we are going to be operating in what you might call a pre-numerical analysis setting, where we are allowed to use real numbers and perform real arithmetic operations. We're not going to worry about round off or floating point error. So this is math, but we are interested in counting the number of arithmetic operations that we perform. We're just not going to sweat whether they're operating on numbers that we can actually store on a physical computer. So that address the question? Okay, good. So let's start with an example which JM has already provided for us. Example 1, suppose we want to verify matrix multiplication. So in this setting, we're going to let A, B, and C be n by n matrices, let's say over the integers, just to keep things simple. I'm allowing big integers, though, because I don't really care about the cost of storing them, or I don't charge you extra to operate on big integers today. And the question that we would like to answer is whether C is the product of A and B. Okay, suppose we wanted to be confident that this were the case. How much work would we need to do?
How confident?
Suppose we'd like to be certain about the answer.
Multiply A times B.
Huh?
We should multiply.
So conventionally, we would probably perform n-cubed arithmetic operations. I know this is going to make some of you angry, but the baseline that I use are standard numerical algorithms, and the fact is that the standard algorithm for matrix multiplication is the one that we use. That's the baseline, even though, of course, we can do this in n to the omega if the matrices are astronomically large. Okay, so here's a different strategy for solving this problem, where we would like to obtain some confirmation, perhaps some support in favor of this identity being true or not. And it involves randomness. So suppose that we choose a random vector x, which is uniform over plus minus 1 to the n. So each of the n entries of this vector is a coin flip. It's equally likely to be plus or minus 1 independently. And we're also not going to talk about where the randomness comes from or the quality. When I write down a probability distribution on the board, you should assume that I get a pure draw from that distribution. Of course, it's a huge question about how we do this reliably in practice, where we get our random bits from, whether or not these random number generators are doing what we think. I don't care today. I mean, actually, I don't care ever, but probably I should. OK, so here's what we're going to do. We're going to multiply the random vector x into C, and we're going to multiply the random vector x into AB. But wait a minute, we don't have AB, so how do we do this? We use the magic of associativity to do this in 2 steps. So we multiply x into B, we multiply the resulting vector into A. How much does that cost? This is only n-squared operations, so this is cheaper than the baseline. It's certainly cheaper even if we believe that this should be n to the omega. And what do we do with these 2 vectors? Yeah, we check if they're equal. So let's start with the other case. Say they are unequal. Then what do we deduce? This identity is false. Do we have any doubt about that? No. So we can assert that the identity is false with an exclamation point because we are confident in our result. Okay. On the other hand, they might be equal. And in that case, what do we report? True? It's probably true. It's probably true, but it's not certain, right? So it could be that we got unlucky and we happened to pick a vector x, which is in the null space of C minus AB, for example. There are other things that could happen as well, okay? So this algorithm uses randomness in a fundamental way. It is potentially a lot cheaper than completing the matrix multiplication explicitly, and it gives us evidence about whether the decision problem has the answer false or true, but it's asymmetrical. Okay? So what we can see here is that this algorithm is correct with high probability. You're going to analyze some version of this algorithm on your homework, a simpler version of this, so I'm not going to do it here for you. But this algorithm can fail. So algorithms that have this flavor are called what type of algorithm? They're called random, but it's a specific flavor of randomized algorithm.
Las Vegas or Monte?
It's Monte Carlo, this one. Yeah. Monte Carlo. So this is different from Monte Carlo approximation, which we'll talk about later.
How high a probability is high probability?
It depends. So you need to bound the size of the integers here, or you need to. So this result, by the way, is attributed to Schwartz and Zippel, and also to DeLillo and Lipton, in which case they prove much more general results. It actually goes back even to the 1920s for finite fields. So this is a long history. It is intimately connected with the development of randomized algorithms. What probability? It depends on what you assume.
But it's always at least a half.
Yeah, should be at least a half.
You can repeat it like a lot.
Yeah, that's your homework.
Okay.
Yeah, good. More questions? Okay, so we've already seen our first randomized algorithm. It addresses maybe a basic problem in numerical and algebra that we don't think about that much, but that we might be interested in solving.
Sorry, how is the half obvious?
It's not, I mean, I've thought about it before, but I think we're proving on the homework, I
Oh,
guess.
okay.
I think there's some counting arguments to tell you that. I mean, you could think about the entries just being 0 and 1, and but it's easier over a finite field, in which case you can.
If you're in the
Yeah.
kernel, there's at most one bit you can flip.
Exactly, yeah, that's the argument.
So
Yeah.
I know you're talking about real numbers and not floating point numbers, but in floating point, that's a hard question to answer, right? Whether they're equal.
Absolutely. That's why we're not talking about floating point. I mean, we just don't need to complicate matters more because there are a lot of important subtle issues. This is not often the kind of question you would seek to ask in floating point, though. This is a bit more of a symbolic computation question, or one that you would be interested in a discrete setting. Whereas in the real setting, you know, if you chose these from a continuous probability distribution, you're not going to get the wrong answer. Okay? So I specifically framed it this way so that there is an explicit possibility that things don't work out. Okay? Good. How about another example, yeah? Okay. We've already done this example. Example 2, the randomized power method. So Mark has masterfully prepared the ground for us to discuss this. I guess I should probably add citation. So this is DeLillo, Lipton, Schwartz, Zippel, 2 different papers. And I attribute this to Kuczynski and Wozniakowski from 1992, although there are precedents, which we can talk a little bit about.
I think this has a name, Freiwald's algorithm.
Freiwald's? Freiwald's? Oh, yes. What's the date? Older? Very,
Because
okay, let's write down Freiwald. I didn't actually do my homework on this.
I think, or maybe it has a D, but it can be Googled.
Okay. Good. Thank you. I admit I didn't do my homework on the references. So,
Collaborative.
and there's potentially a lot of argument about the source of this particular algorithm for the reason that, as Mark mentioned, since time immemorial, numerical analysts have been using random starting vectors for the power method. But good. So what's the setting here? We're going to let A, by the way, 2 underscores means a matrix, 1 underscore means a vector, just since I can't write boldface on the board. So we're going to let A be an n by n PSD matrix. And we should assume it's non-zero to avoid some boring problems. H stands for Hermitian. The R means that it is a real valued Hermitian matrix. So it equals its transpose. And the question that the power method seeks to answer is to approximate the maximum eigenvalue of A. Why approximate? Well, it's Abel's theorem, right? We know that there is no finite algorithm that does elementary operations and produces the correct answer in general. Okay? So we have to do something iterative. And Mark didn't mention this morning, but surprisingly, the power method is an algorithm from the modern era. It dates to the 1930s. It's not part of the lore of numerical analysis dating back to the pre-mechanical age.
Why do you have to approximate? I mean, I understand.
Why do you
matrices are
have
big.
to?
What theorem did you quote is my
I said
question.
Abel's theorem. This is, okay. So the connection with polynomials tells you that you're not going to compute the maximum eigenvalue, which is a root of the characteristic polynomial and a finite number of elementary operations and radicals, yeah? Okay.
Well, but really,
Okay.
you can't compute the square root of 2 either, right? I mean,
All right, I really don't want to argue about this, if you don't mind. So the assertion is that we are interested in the maximum eigenvalue of an Hermitian matrix for some of the reasons that Mark described earlier. And we are going to use an iterative algorithm to approximate the maximum eigenvalue. And maybe you secretly know a finite algorithm that can do this, but I don't. All right, so what's our strategy? So because this is a self-adjoint matrix, what do we know about its eigenvectors? They're orthonormal, yeah? Okay. Do we know what they are? No, we don't. Because if we knew the eigenvectors, we'd be done, okay? So we're going to use randomness to somehow weasel our way out of this trap. So we're going to draw a random vector x from the normal distribution with mean 0 and with identity covariance. Again, I'm assuming we can draw exactly from this distribution and that we can work with real values here on the whiteboard. Okay? Now, why is this a good choice? So what properties does this normal distribution have? Geometrically.
It's rotation invariant.
It's rotationally invariant. It's indifferent to the basis of the space. Okay? So in particular, it doesn't care whether your eigenvectors are pointing this way or this way. I can't move my right arm higher than this these days, but and so that's why this is a good choice. It's indifferent to the eigenvector basis of the matrix. It just doesn't care. Okay? So we're taking advantage of some symmetries in this problem. And the way the power method works is by computing a guess VT for the maximum eigenvector by multiplying the initial vector x into A repeatedly. Okay? So we do this by repeated multiplication the same way we did here. And so this amounts to T matrix vector multiplies with A. So we assume that we have this primitive access to A. We think about A as like a data structure with methods attached to it. And the method that we are allowed to use here is the one that says a.matvec, which takes as an input an x and reports A times x. This is the only way we're allowed to interrogate A in this context. So we are driving the initial vector toward a maximum eigenvector, as we saw in Mark's talk. X with probability 1 has a component in the direction of the maximum eigenvector. And so for sure this is going to work. Now, we're not actually interested in eigenvectors for this problem. We're interested in eigenvalues. So we're going to form an eigenvalue estimate, which I'm going to call Ct plus 1. And I'm going to do that by computing the inner product between Vt plus 1 and Vt, and dividing by the norm of Vt squared. And this can also be unrolled to obtain the following Rayleigh quotient. And so you can see there's an extra A up here as compared with the denominator. And so this is the Rayleigh quotient of some vector Vt with the matrix A. Okay, so we think this is going to be a pretty good estimate. And following on Mark's analysis with probability 1, the inner product between x and the first eigenvector of A is not 0 with probability 1. So we can deduce that the eigenvalue estimates converge to the maximum eigenvalue with probability 1. Okay. This is not an algorithm because it is an iterative process potentially without end. To convert this into an algorithm, we need a stopping criterion. Okay? So I'm not going to talk about stopping criteria. This is a whole thing. But using the data that we have, Vt and Ct, we need to decide when to stop. That has to be built into the algorithm. And what's interesting is that the number of steps it takes before the stopping criterion is triggered is a random variable, because we are starting with a random vector. Okay? So algorithms that have a runtime that's random are called Las Vegas algorithms. We don't see these very often, but this is an example. The randomized power method, where we start with a random standard normal vector and run until we trigger some stopping criterion, has a random runtime. It's a Las Vegas algorithm. Okay, we'll talk a bit more about the analysis of this later. Yeah. U1, this is the maximum eigenvector of A, which I did not notate on the board. Yeah, I said it out loud, though.
Is there any
Yeah.
reason we have these names, Las Vegas, Monte Carlo, other than
The whimsy of computer scientists? I actually don't know. So the name Monte Carlo in the context of randomized algorithms, we'll see some like pure Monte Carlo algorithms later. This is attributed to the physicists Ulam and Metropolis, who developed these algorithms to do rather complicated calculations involving neutron diffusion for reasons that you probably know.
This is pure speculation, but I thought Las Vegas came from the expression like the house always wins. Like you keep playing randomly, but eventually the algorithm gets it right. That's what I always.
They also
Monte Carlo.
They also have casinos in Monte Carlo.
But yeah.
That's what I was asking.
Yeah, I don't know.
Okay, good. Questions about these two examples? So we found linear algebra algorithms that exemplify the two basic types of randomized algorithms.
This is like, I don't know if you look at, but usually Las Vegas algorithms, they have to be correct when they stop.
When they
I don't
stop?
think there's a stop.
Yeah, but the stopping criterion, right, is triggered, and that is the definition of correctness in that case. Although you have to be careful because you can't be certain that you get the maximum eigenvalue at that
that's
point.
what I
So
mean.
yeah, so I am sweeping something under the rug here. That is, admit I actually expected someone to pick, but yeah. Okay, good. Questions about these examples? All right, okay. So here's what we're not talking about: statistical randomness. So I think it's really important to draw the distinction between the use of probability, randomness as an algorithmic resource, versus statistical randomness, where we use probability for one of several things: to model problem instances. I'll give you some examples in a minute to make it clear what we're talking about, or to describe the nominal behavior of an algorithm. Whoa, let's try that again. Okay, so what are some examples of statistical randomness? So example one, average case analysis. And so this is when you place a distribution over the problem instances. And you ask what the performance of the algorithm is in that setting. So for example, you want to sort some numbers. You assume that the numbers are listed in some random order. Okay? And then the question is, how long would your sorting algorithm take for that instance chosen from that natural distribution? This is not what we're doing. We are assuming that the instance is given, you are stuck with it, and your algorithm gets to make the random choices, but we're not assuming anything about the nature of the instance. Okay. There are some settings, especially in machine learning, where it is reasonable to assume that they're problem instances. You see new instances over and over and over again. You can start to build a distribution. You can try and design algorithms that take advantage of that distribution over the instances. But I don't think it's reasonable to say, suppose that my matrix A is a Wishart matrix. How does my algorithm for computing maximum eigenvalues behave? I don't need to solve that problem because I know the maximum eigenvalue of a Wishart matrix. So that's not what we're doing here. Someone hands me A, I got to find its maximum eigenvalue. Okay? Example 2, smoothed analysis. So what is smoothed analysis? Smoothed analysis is when we make a random perturbation of the problem instance. So for example, a matrix might lead to large pivot growth when we apply Gaussian elimination. If we poke the matrix, maybe the pivots don't grow so fast anymore. Or we're interested in diagonalizing a matrix. The matrix that is handed to me is a bad matrix, but nearby there is a good matrix. So smoothed analysis is asking about what happens for a random modification of the problem instance. So we can ask about either the stability of an algorithm or else the conditioning of the underlying computational problem. You can convert this into an algorithmic strategy by randomly perturbing your problem instance, which is interesting. So there's a duality here. But at least at a high level, the question the smoothed analysis is initially seeking to ask is, near my fixed problem instance, what do things look like? Okay? So that's an example of using statistical randomness to model the local behavior of an algorithm. Okay? There's one more example that we see a lot, which is rounding errors. So as you know, when we do algebra on a computer, we have to use floating point arithmetic or some other mechanism for storing the numbers, and we often have to round off. And when we round, we make errors. And so the question is, what do those errors look like? One thing you might do is assume that the errors are random numbers. This is not true, but it didn't stop people from positing this model. And in fact, it appears in some of the earliest papers on numerical analysis. So back in 1951, Goldstein and von Neumann wrote a paper about LU decomposition of a matrix. They understood that they were going to incur numerical errors when implementing this algorithm. They wanted to know the severity of those errors, so they modeled them as random numbers, and they bounded the size of the error incurred by those random errors. Now, the fact is that random models for floating point errors are not so simple or accurate, and this is not something we're doing. We're not assuming that the behavior of the algorithm has some statistical performance, which we've just kind of invented as a simplifying assumption. On the other hand, by duality, you can implement stochastic rounding procedures where you are literally making random decisions when you round your numbers to take advantage of the probabilistic phenomena. So people do that. It's popular these days. Some of Nick Hyam's latest papers were on exactly this subject. How do we analyze stochastic rounding? How do we understand its benefits? But these are all examples of models that we are placing on problem instances or on algorithm behavior, and that's not what we're doing here. Okay. Yeah, Jim.
Just to note that the new 8-bit floating point standards committee is likely to add stochastic rounding to the standard.
There we go. So again, that's not modeling rounding errors randomly, but insisting that the rounding errors are random. Yeah? So that's a good thing, but the model is questionable unless you enforce it. Okay, good. So here are things we're not doing, and I guess there's one other valuable point here, which is that randomized algorithms produce statistical output because they're random. And so you can use statistics to design better algorithms if you want. So let me write that down. Randomized algorithms have statistical output. And so we can use statistics to understand the output or to design better algorithms. So I'm going to give you the simplest example of this, which I hope you have seen, and that is the majority vote procedure. So here's the setup. Suppose we have a randomized algorithm for a decision problem. What's a decision problem? The answer is yes or no. Okay? And we're going to assume that it gives the correct answer with probability p, which is a number strictly bigger than a half. Okay? So the algorithm is guessing, but more likely than not, it's right. Okay? Now, this is maybe not very inspiring if the algorithm is only correct with probability 51%. So what are we going to do? We're going to run the algorithm repeatedly with independent randomness to achieve a lower failure probability. So we achieve failure probability delta in 0, 1 by performing n bigger than 1/2 p minus 1/2 minus 2 log 1 over delta independent trials, and take a majority vote. So if we run the algorithm over and over again, we can enjoy the wisdom of the crowd and push the failure probability down as low as we want. And what's interesting is that we can make the failure probability very small with a rather small number of trials. Okay? Although it does depend on how confident the algorithm is. So if the probability of success is 51%, we're going to have to pay a lot more trials to gain high confidence. Okay, good. So this is an example of using statistics to improve the output of a randomized algorithm. In this case, it's simply repeating a statistical experiment over and over again to become more confident in the result of that experiment, which is the foundation of empirical science. Okay. So this is not our focus either, but I think it's important to be aware that when the output's random, it requires you to think about what the output means. It's not yes, I am certain, or no, I am certain. It's like, I think the answer is yes, and I need to understand how to interpret that information and perhaps how to gain additional confidence in the outcome. All right, good. So the first thing I'd like to do is talk about a theme which is inspired by the randomized power method, which is the basis for a number of important spectral computation algorithms. So let's come over here. And that theme is algorithms that choose a random starting point. So I'll find this in the notes. Okay, so theme 1. Random initialization. So the idea here is that we start an usually iterative algorithm at a random point to make a favorable trajectory likely. So the example is already here on the board. So to understand the randomized power method, it's convenient to study the relative error. So we'll define the relative error in an eigenvalue estimate xi to be the maximum eigenvalue minus the estimate divided by the maximum eigenvalue. Okay? So we're asking for the error relative to the correct answer. And because xi, the estimate that comes out of here, is a Rayleigh quotient, it's always smaller than the maximum eigenvalue. So we can be confident that this is a positive number. Okay? So we'd like the relative error to be small. And one of the interesting features of using a random standard normal vector as a starting point is that we can achieve a result which, to the best of my understanding, was invisible to the classical analysis. And that is the following. Even without a spectral gap, so we don't need to assume that lambda 2 is smaller than lambda 1. Even without a spectral gap, we can determine that the expected error after t steps is less than 1 over t times 1 plus log square root 2n plus log t, where t is the number of iterations of this method. Okay? So without any assumptions on the matrix, aside from it being positive semi-definite, we can bound the relative error after t steps on average. Okay. And so, like I said, to the best of my understanding, there is no classical result that identifies the correct performance of this algorithm without assuming that there's a gap between the top eigenvalues and one of the lower eigenvalues. This always works. Now, There-
Let me just interject
Yes.
to say one difference of this analysis from
Yes.
what I showed is that I was looking at angles between vectors,
Yep.
right? And so with no spectral
Right.
gap, you could have two eigenvectors.
And in fact, without a spectral gap, we can't solve your problem
Right, exactly.
because of Davis-Kahan, right? So there's a sleight of hand here in that we are only interested in the eigenvalue, not the eigenvector. And there's also a disappointing, sorry, what, Jan?
What goes into proving that?
It's in the lecture notes. There's an explicit formula for the error, there's a Gaussian integral, there's some bounds.
I don't want the
Yeah.
proof, I want the idea.
What's the idea? The idea is you write down a formula for the error. The projection of the maximum of each of the eigenvectors onto X is about the same size, and then you massage the formula to see that.
So you're guaranteed to move at least
Uh,
a certain amount each step.
Yeah, you
towards
make
your
progress at each step, regardless of what's happening.
goal. And it's always monotone.
So what happens if there's no spectral gap is that there are a bunch of big eigenvalues, and if that's the case, you actually have more success because there's a bigger space that you can attract to and still get good estimates. So it actually in some ways makes it easier.
They all have the same Rayleigh quotient. all
Right, they have the
different
same, or almost the same Rayleigh quotient. And that's the point here. We're only interested in the Rayleigh quotient. We're not interested in whether we found a single correct direction. Okay? But this is what the randomness gets you. And there are a few interesting features here, which is that there is a burn-in. We need to take log n steps before anything happens. Okay? So if t is not bigger than log n, this bound is vacuous. Okay? This is a real phenomenon that you can see when you run these algorithms. If you don't run them for a certain number of steps, there's no information. You can also see that the error only goes down like 1 over t, which is sad. This is a polynomial rate, not an exponential rate like Mark's analysis yields. And that's the price you pay for not making this assumption about the spectral gap. The spectral gap is what allows you to obtain exponential convergence. But on the other hand, there are no conditions here, which makes this a very powerful fact about finding maximum eigenvalues. Okay, so there are a bunch of related methods that do similar things. So there is the randomized Lanczos method, which is also studied in this paper by Kuczynski and Wozniakowski, which gets a t squared here. So it converges significantly faster, and is based on similar ideas.
It's not like gradient descent, right?
What?
It's not like gradient
It
descent.
is a lot like gradient descent, although I think it's important to note that even though the published rates here look like the optimal rates for optimization algorithms, the linear algebra algorithms are doing something different, right? Because the ones involving Krylov subspace are doing polynomial approximation, and they destroy methods based on optimization. So this is not really optimization, even though the rates look similar.
Also, the dependence on the dimension, the log n doesn't show up for convex optimization. That's a big.
Yeah, okay. So this is a spectral method that's trying to find maximum eigenvalues and eigenvectors. There are also algorithms for low-rank approximation, which do the same thing. They start at a random block of vectors, and they drive that toward a matrix that's well aligned with the range of the input matrix. So these are algorithms like RSVD, randomized SVD algorithm, randomized subspace iteration. So this is the algorithm Mark talked about this morning, except you start with random vectors and exploit that in the analysis. And randomized block Krylov iteration, where you build a Krylov space using a block of random vectors. This is something that Cameron and Chris obtained the first analysis of. These are all examples of algorithms that work because you start at a good random choice and drive it toward a better future. Okay, good. Questions about this theme?
Trying to remember RSI.
Randomized subspace iteration. Yeah.
Randomized EK.
Block Krylov iteration.
What's the singular value?
Randomized singular value decomposition. Yeah, so these guys are studied in HMT 11. So all of these references that I write on the board are to the bibliography of the arXiv paper. And a good reference for this is Musco and Musco 15. Sorry, it's hard to write this slow down. Yeah, for sure.
So most of what you wrote there is where there's a low dimensional amount of bad things that you're trying to avoid, but then the low rank approximation, like low rank matrices, are themselves something that is of positive codimension. So could you?
So I should be more precise. The goal for low rank approximation is that someone hands you a matrix A and you would like to approximate its truncated singular value decomposition. You would like the best low rank approximation of the matrix with a given rank.
I see.
So obtaining that exactly is hard for the same reasons as it's hard to compute maximum eigenvalues exactly, but you can make good approximations of this.
I see. So low rank is part of the problem statement.
Yeah. So when we say low rank approximation, what we mean is find a low rank approximation of a fixed matrix.
Okay.
And because we're only interested in the approximation error, we don't run into this problem that it's hard to identify invariant subspaces accurately when there are no spectral gaps. These algorithms don't care because they're only interested in the quality of approximation, and there are potentially a lot of approximations that give the right answer.
Right. There's a big region that has the same.
Yeah. So I'm not going into the details here because it's a relatively short presentation, but these all work for the same reason, roughly. It's because you started at a good random point, which is well aligned with the things you care about and is oblique with the things you don't care about. That's what's happening here too. The normal vector is aligned with the first eigenvector, at least a little, and it's not too much aligned with any of the bad eigenvectors that you don't want. Okay. Good. So,
Do you care that it's not too much aligned with the other eigenvectors?
you do. It makes a difference. Yeah. The classical analysis does comprehend this because it's usually expressed in terms of tangents of angles between the leading subspace and the counter-leading subspace, but it appears pretty clearly in the analysis. Okay. So why stop with the first iteration? So the next theme is progress on average. So in this case, we use randomness to decide where to start, and that was it. The rest of the algorithm is deterministic. In this case, at each step in an iterative algorithm, we will use randomness to try and make a bit of progress. So iterative algorithms make random choices at each step to make progress on average. So we've already seen an example of this, and that's the example that I'm going to use just for conceptual simplicity. But before I do that, any of you know an algorithm that has this quality? It is currently the most popular algorithm in the observable universe, stochastic gradient descent. Yeah. So this is an optimization algorithm rather than a linear algebra algorithm. But this is exactly what it does. At each step, we take a step in the direction of a random vector, which looks like the gradient, negative gradient on average, and hope that that helps us get toward the bottom of the hill. It should also be said, by the way, that random initialization has some important classical applications in optimization, one of which is to find yourself in the domain of attraction of the optimal point. Another example is to avoid landing on a bad submanifold that will take you somewhere that you don't want. So there are a bunch of ways that people use this for optimization algorithms, but optimization's hard. I prefer to stick with linear algebra, which I understand at least a little. Okay, so the example of the progress on average paradigm we're going to talk about is randomized catch-marts, K-A-C-Z-M-A-R-Z, for overdetermined least squares. And the analysis of this is due to Stromer and Verschinen from 2009, although this is really just a special case of stochastic gradient, and the analysis really goes back to Robbins and Monroe in 1952. Okay, so what's the setup for this? So we're interested in a matrix A, which is tall. So it's got a lot more rows than columns. We're going to assume for simplicity that it has full rank. And we'll write its rows as AI conjugate transpose. There are no complex numbers here, so don't need to sweat this. And we're going to assume that the right-hand side of the least squares problem B actually belongs to the range of A. So this is a consistent problem. If the problem is inconsistent, this algorithm doesn't do what you expect, and you need to be more careful. And so the goal here is to solve the minimization problem, minimize over x in Rd, ax minus b, Euclidean norm squared. Okay? So we're looking for the x that explains b, and in this case the error is 0 because I've assumed that b is in the range of a. Okay? So it's a consistent overdetermined least squares problem. So where do these kinds of problems turn up? Well, usually they are inconsistent. So this algorithm needs to be modified for practical applications. Places where you see inconsistent least squares problems with a lot of rows are computed tomography, where you're taking a lot of measurements of someone from different directions. It comes up in some signal processing applications. There are a few examples where these problems are natural. And I will describe the catch-marts algorithm for you briefly. And we'll talk about why it works and how it fits into this template. Okay, so what does this problem look like? We've got A. We're looking for a short vector x to approximate the right-hand side B. And what the randomized catch-marts method does at iteration t is it's going to select a random row of the matrix and enforce that equation exactly. So we start at a vector x naught, which can be as bad as you like. And then we pick a random equation, I of t, and enforce it. So the formula is something like this. The next iterate is the previous iterate minus the inner product between ai, I'm suppressing the t here, and the previous iterate, minus the ith coordinate of the right-hand side, divided by the squared norm of the ith row times the ith row. Okay, so this is what we do at each step. And you can check that the ith equation is enforced perfectly after making this update. Okay, maybe you screwed up the other equations, who knows, but at least this one's right. So small victory. Now, how much does it cost to solve a overdetermined least squares problem? The classical algorithms are ND squared, based on, for example, QR factorization or SVD. Again, we are not using fast matrix multiplication. How much does it cost to perform this step? Well, we're operating on vectors of length d, and so this is really just order d arithmetic operations. So this is pretty cheap. We can do a lot of these iterations. Okay, so there's one more valuable idea here inside catch-marts, which is importance sampling. So how do we decide which row we want to pick? What's good? Well, the idea is that equations that have more energy are more important, and we should enforce those preferentially. So we're going to pick the random equation in proportion to the squared L2 norm of the row as compared with the sum of the squares of the row norms. This is an honest to goodness probability distribution, and this term here cancels this term, roughly speaking.
Then we have to pay a price.
Yeah, that's a great question. So you need to pay a price to compute this. So that is a pre-computation step, or else you use something you understand about the problem. So if you're solving a computed tomography problem, you might be able to use the physics of the imaging system to understand what the row norms of these things look like. If this is just some data matrix, yeah, you got to just go for it. Okay. Good. So we have an importance sampling distribution, which we have to compute. I'm not charging you for that, though. And the analysis, which is not very hard and is on your homework, is the following. So
it is like order of ND, right?
What?
The denominator.
It is if you have to compute it explicitly.
I guess you're
Yeah.
supposed to do this the same A many times.
Yeah. I'm not going to charge you for this. I'm going to be generous. For you, my friend, it is free. Okay, so how do you analyze this? There is a optimal solution, X star in RD, and we'd like to know how far away we are from the optimal solution after we've taken this step. And the analysis makes the following bound. We get 1 minus 1 over the Demel condition number squared. I will remind you what this is in a second, times xt minus 1 minus x star squared. So as compared with the previous iterate, we reduce the error on average by a factor that's smaller than 1. And the Demel condition number is the Frobenius norm of A divided by the minimum singular value of A, which you can also interpret as the D times the average singular value divided by the minimum singular value, just like we heard yesterday. Okay? The important thing here from my perspective is that this number is not infinite. So we are actually making a constant factor reduction of the error at each step. Okay. Now, this is just one step. So what happens if we repeat? The reduction multiplies. So we are going to converge exponentially fast to 0 error. And the rate is determined by this conditioning of the matrix. Okay? So this is progress on average. At each step, we might do a garbage job. But on average, we're making progress. And what that means is that on average, after a lot of steps, even if we make some mistakes, we will correct those mistakes and we will eventually, on average, converge at an exponential rate to the optimal solution. So this is the progress on average paradigm. Okay. So I don't think I'm going to belabor how many iterations you need to do this. The point is that the iterations are pretty cheap, and when the condition number is small, you might not even need to look at the whole matrix, which is fair because these equations are redundant. They're telling you the same thing over and over and over again. Why do you need to look at all of them? Who cares?
Is it also like an instance of method of alternating minimization? You can see it that way, like you try to fix
Yeah.
one row and then the next, but the one that back and
Yeah.
on.
But you're still making progress.
Yeah, but
Yeah.
but also in alternating.
Yeah,
minimization.
alternating projection does something similar, except that it's not really
Sometimes it can be
randomized.
analyzed.
Yeah, so that's actually a deterministic algorithm, right? You're just bouncing back and forth between, say, two convex sets or something, and the distance is decreasing, but you're not making a random choice.
Could you confound it by giving it a matrix with a huge N that has D different rows, one of them repeated n minus D times, and then you're almost certainly picking the same row to correct against every time?
Yeah, that's going to be reflected in the condition number being big.
Oh, okay.
Yeah.
Okay.
Yeah. So I guess one other interesting point is that what do you call a sequence that has this property? It's called a positive super martingale. Okay, it's very confusing. Super martingales go down, sub martingales go up.
Superman, as I remember.
Superman goes down.
Superman goes down, yeah.
Superharmonic functions, that's the connection. But yes, so what that also means is that for these kinds of algorithms, you can use martingale inequalities to understand their evolution. And in particular, Dub's theorem tells you that the error relative to the exponential rate of convergence ultimately has a limit, which is a random variable. And so there really is a strong sense in which this algorithm converges exponentially. Martingales are awesome.
So the expectation
Yeah.
is actually a conditional expectation, all right? That's why, I mean, then I see martingale and otherwise. I didn't notice, right? What's this?
Didn't know what.
That is a conditional expectation.
This is conditional. I'm only averaging over IT.
Only.
Yeah. All the previous choices are fixed. At each step, I pick a new row at random, independent of all my previous choices. Yeah.
So yes, it's
It
conditional.
is conditional on IT minus one and all the previous row choices. Yeah, sure.
If you do this on a system that does happen to be inconsistent, are you guaranteed to discover this quickly?
Yeah, I actually don't know the answer to that. If you run this on an inconsistent system, it converges to some usually some radius of convergence around the optimal answer to the least squares problem, but it doesn't get you the right answer. You have to work harder if you want the right answer.
Okay.
There are other
Be very
algorithms.
close to something.
Yeah, no.
So if you don't want to use randomness and you just decide you cycle in some, not cycle in some order, do you
Yep.
get anything?
Yeah, it's extremely hard to analyze this algorithm if you don't make, so if you use a deterministic anything. So the best version of this algorithm is actually randomly permute the rows, then cycle. Okay. This is extremely hard to analyze though, and it's not, I actually don't know a good resource for that, but empirically that's the best thing to do. One random permutation followed by cyclic control. Yeah, Raphael.
Conceptually, if I have a perfect system that is consistent, why do I care about some rows having higher energy than other rows? It's just about like, I can scale the row of A and the corresponding row of B by a factor. Doesn't change anything in terms of...
Yeah, it's a mystery.
Okay.
It shouldn't make a difference. I mean, so I mean, that's another thing you do. You can precondition the problem by normalizing all of the rows and normalizing B, and that will also change the condition number.
Oh.
Yeah.
Sure.
Hi.
Do you want to make a break soon? So
Yeah,
we take
where
one
are we right
question
now?
And then we,
Yeah, it's been an hour. Okay, I want to write one more thing on the board, and then we should take a nice break. And that is more examples of this paradigm, and that's it. So just say 2 words about the names of these things without any further description. So other examples of algorithms that do this are sketch and project methods. We haven't talked about sketching yet. There's a very nice paper by Gower and Rikhtarik from 2015. At each step, you sketch, you solve a problem, you make some progress, you repeat. And another algorithm of this flavor is randomly pivoted Cholesky, which chooses a random pivot in the Cholesky algorithm to try and produce a low-rank approximation of a positive definite matrix efficiently. It also makes progress on average at each step, but the analysis is much more involved. OK, great. Let's take a break. And then after we've had some coffee, which I can see you sorely require, we'll talk about some more themes.